Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome to the deep dive. Today we are cracking the code on a piece of networking magic that absolutely has to work perfectly for you to even be hearing my voice right now.
That's right.
We're talking about the ultimate undercover translator that makes our data packets move.
And, we live in a world defined by those elegant numerical handles IP addresses. They define the logical destination, on the global internet.
Right.
But the truth is, when devices are talking to each other locally on your own network, they only understand physical addresses, those 48-bit MAC addresses.
And that's a huge disconnect, isn't it? You have the logical world of IP versus the concrete world of physical hardware.
Exactly.
And this essential bridge is the Address Resolution Protocol, or ARP. So our mission today is to really pull apart the mechanics of ARP, understand its variations, and see why it's the engine that sits right between the internet and data link layers.
And here's the key fact we're building on. ARP's core task is converting a 32-bit IP address, specifically for IPv4, into that corresponding 48-bit MAC address. It's the translator that turns the name of the destination into the actual door number on the local street, so to speak.
Okay, let's unpack this then.
Yeah.
What exactly is ARP?
Well, simply put, ARP is the mechanism used to find the physical or MAC address of a device when your system only knows its logical network ID. Its IP address.
And this is vital anytime one device wants to talk to another on the same local network, or LAN.
Right. And if we had to execute that lookup process every single time a host sent a single packet, your network would just crawl.
It would be unusable.
Utterly. So efficiency is the name of the game. And what's fascinating here is that every operating system in an IPv4 network maintains an ARP cache.
Yeah, the ARP cache, think of it not just as a phone book, but more like a short-term memory system. It's a table where your computer stores IP to MAC pairings it just learned.
So it doesn't have to ask again immediately. When your computer needs a physical address for a specific IP, it checks this cache first. If the mapping is already there and it's fresh, meaning the IP address is already bound to a specific MAC, it just bypasses the whole resolution process.
Saving milliseconds and preserving bandwidth, it's essential for network speed.
It really is.
But, speed comes with the dilemma. If that mapping stays in the cache forever, it could become stale. What happens if a device changes its location or its network card is swapped out?
And that leads to the critical timing decision known as the ARP cache timeout. This is the designated duration for which that MEC address is allowed to reside in the memory table. If the timeout is too long, you risk using an incorrect, stale address. If it's too short, you're just constantly generating unnecessary network traffic.
So network engineers are always optimizing this trade-off between speed and accuracy just to make sure those tiny cache tables are useful but not, misleading. It's a constant silent struggle.
It truly is.
Yeah.
It highlights that this whole concept of local network address resolution isn't a one-and-done deal. It's a constant negotiation.
That sets the stage beautifully. So we know the cache handles the easy cases, but when the cache fails or when a host is new, we need that dynamic resolution process. Let's follow a data packet and see how the lookup works step by step. Because often, the host isn't talking directly to the final IP address, is it?
That is the single most important clarification we can make. When a host sends a packet outside its immediate subnet, it does not resolve the MA address of the final destination IP. It only resolves the MAOC address of the next step, the next router in the path.
Okay, so let's use the classic example. Say we have host P, and it wants to send a message to host U. Host U is far away across, let's say, two intermediate routers, T1 and T2.
Right. P does not try to find the MAPT address for you. That would be impossible.
It's too far away.
It is. P's job is much simpler. It looks at the destination IP, which is U, and realizes that U is external. Therefore, P needs to send the packet to its default gateway. Let's call it T1.
So P's actual job is just finding the physical address of T1. It's like a delivery person being told to send a package to another city, U, but they only need to know the address of the regional sorting facility, T1.
Exactly that. The network layer on host P takes the packet, which is still addressed logically to U, and wraps it for delivery to T1. P then checks its ARP cache for T1's MAC address, if it's not there.
Then it initiates that dynamic resolution process.
Right.
Which means P sends out an ARP request.
Correct. The ARP request is essentially a broadcast. It's P yelling into the local network, hey, who has the IP address for T1? If that's you, please tell me your MAC address.
And every device on that local segment hears it.
They do. And T1, which is listening, recognizes its own logical IP address in that request.
And that's the trigger.
That's the trigger. T1 receives the broadcast, sees the request is for its IP, and immediately sends back a unicast ARP response or an ARP reply directly to P.
And that reply says, I am T1, and here's my 48-bit MAC address.
P receives that reply, adds the IP to MAC mapping for T1 into its cache for future use.
For efficiency.
And then frames the original packet for immediate physical delivery to T1.
And then T1 takes over.
T1 receives the packet, strips off the physical addressing, looks at the destination IP, which is still U, and realizes U is still external. So it decides the next hop is T2.
And it repeats the whole process.
It repeats the ARP process to find T2's MAC address, forwards the packet, and then T2 finally delivers it to you. This entire flow just hinges on ARP efficiently resolving the MA of the immediate next hop.
It's incredible how many little handshakes and translations have to happen just to move a single piece of data across a couple of routers.
And that IP to MEC association we just discussed, that is what we call binding. And we should probably explore the 3 distinct ways this binding can occur, because it's not all dynamic ARP requests.
Right, we've already covered the first one, haven't we?
Yes, the first is table lookup. The bindings are already stored, either statically, meaning manually configured by an admin, or dynamically through the ARP cache we discussed.
The protocol address is the key, and you get the hardware address.
Right. This is all about speed and pre-storage.
And the dynamic resolution is the ARP request reply we just detailed.
That's the second method. Dynamic resolution is the just-in-time approach. The data link layer sends that request message across the network in real time, and the destination device responds. It's the most common method when the cache misses.
Okay, but this third method sounds a bit obscure. Closed-form computation. How does a device calculate an IP from a MAC, or vice versa?
It's highly specialized. You usually only find it in closed or proprietary systems. In this scenario, there is a predefined mathematical relationship between the hardware address and the protocol address.
Like a formula?
Essentially, yes. For instance, in some embedded systems, the protocol address might literally be derived from a part of the hardware address.
So instead of looking it up in a table or shouting for it, the device just runs a simple algorithm. But this only works if you have absolute control over the addressing scheme.
Precisely. It eliminates the need for any complex address management protocols like ARP because the address is self-contained within the hardware identity. It's an elegant solution, but for very specific controlled environments. Utterly impractical for the open, messy internet.
That level of flexibility is amazing, though, that it's built right into this seemingly simple protocol. But standard ARP request reply doesn't cover every scenario. And here's where it gets really interesting. There are 4 distinct flavors of ARP for special situations.
These different flavors are essential for adapting ARP to complex routing needs and network maintenance.
Let's start with Proxy ARP. This one involves a third party acting on behalf of another device. Why would a router need to impersonate someone else?
Proxy ARP allows Layer 3 devices, like a configured router, to respond to an ARP request on behalf of a target IP address that it knows is in a different subnet. The router responds by mapping its own MAC address to that target IP address.
So if I ask for host X's MAC and host X is, say, across the river, the router says, I'll take that package, send it to me on the next hop.
That's the idea. It allows devices on separate physical segments, which are unaware of the routing boundary, to communicate as if they were local. All the traffic just gets routed through that proxy router. It can simplify subnet management in older networks.
But it can also be a source of confusion, I imagine.
It can. Next up is Gratuitous ARP. That name suggests it's not strictly necessary for communication. What's its use?
Yeah, what's a gratuitous request?
Gratuitous ARP is crucial for proactive network maintenance, specifically for addressing conflicts. When a host or router comes online, it often sends an ARP request for its own IP address.
Wait, it asks for its own MAC address. It already knows that.
It does. But the packet serves two purposes. First, if another node responds, the host immediately knows there is an IP address conflict on the network.
Ah, a duplicate IP.
Exactly. It should shut down or request a new address. Second, the Gratuitous ARP response automatically updates the ARP caches of all other devices on the network, ensuring they have the latest IP to MAC mapping for the newly active device. It's a proactive announcement. I'm here and I'm clean.
That's a really smart self-check mechanism. Okay, now for the two reverse protocols. We have reverse ARP, RRP, and inverse ARP. They sound almost identical.
But their applications are vastly different. They flip the script. Standard ARP goes IP to MAC. RRP, or reverse ARP, goes MAC to IP.
Okay.
It's used by a client system in a LAN that knows its own physical APC address, but needs to request its logical IPv4 address.
So an old system boots up and says, here's my body ID, but I need my network name.
Precisely. RRP was commonly used in older diskless workstations that didn't have storage for configuration files.
Sure.
It relied on a central RRP server that maintained a table mapping AXI to IPs.
Which the network admin had to manually maintain?
Yes.
And inverse ARP, inner RP, where does that fit in?
InRP also resolves AM to IP, but the context is different. InRP is critical in Layer 2 virtual circuit environments like frame relay or ATM networks. In these systems, you establish a virtual connection identified by a data link layer address, Layer 2 ID. Once that connection is established, the node needs to use inIRP to find the Layer 3 IP address associated with that existing Layer 2 virtual circuit ID.
So RRP is about initial assignment for boot up, and InRP is about linking a pre-established Layer 2 path to its Layer 3 identity. They both go backward, but RRP is client-server, and InRRP is path-centric.
That's the cleanest way to distinguish them. Now that we've established how robust and necessary ARP is, we have to talk about its fatal flaw.
Yes, here's where it gets really crucial for anyone who manages a network or cares about security, because ARP is built on a fundamental trusting assumption.
And that trust can be entirely broken. The biggest technical weakness of ARP is that it is fundamentally stateless and trust-based.
Stateless and trust-based.
ARP requests are broadcasts, and ARP responses are generally accepted without validation. There is no handshake mechanism, and crucially, there is no authentication.
Which means if host A asks for router R's MAC address, and a malicious host M sends a reply first, host A will believe host M even if host M is lying.
And this forms the basis of ARP spoofing or ARP poisoning.
Right.
The attacker, host M, sends a fabricated, unsolicited ARP response to host A, claiming that the IP address of the router, R, actually belongs to host M's MSC address. Host A then poisons its ARP cache with this incorrect malicious entry.
And what's the devastating effect of that poisoning?
It enables a man-in-the-middle attack, a MITM attack. Since host A now thinks host M is the router, all traffic destined for the outside internet gets routed straight to the attacker.
Oh, wow.
M can then read, modify, log all of A's traffic passwords, session cookies, everything before forwarding it on to the real router.
So the attacker becomes this silent interceptor, literally lying to the victim's address book and inserting themselves into the middle of the conversation.
And the attacker must also simultaneously poison the router's ARP cache, telling the router that the victim A's IP address belongs to M's MA address. Once both caches are poisoned, the attacker M sits perfectly between A and R, intercepting all traffic both ways.
Yeah. The terrifying thing is that ARP was designed for simplicity and speed in a local network that was, assumed to be safe. It never envisioned this level of malicious internal intent.
It's a core vulnerability that has led to a whole industry dedicated to detection and prevention. Network intrusion detection systems often look for telltale signs of ARP poisoning, like receiving multiple conflicting ARP responses for the same IP.
And the primary way to mitigate this is using tools that implement dynamic ARP inspection, or DAI, right?
That's the key technical fix. DAI validates ARP packets against trusted bindings established by a DHCP snooping database. If an ARP response comes in claiming an unauthorized IP to MAC binding, the switch just blocks the packet.
It enforces a layer of authentication that ARP itself is missing.
It forces that trusted environment back onto the protocol, yes.
That security segment really gives context to why we care so much about this otherwise hidden protocol. Let's finish by just briefly looking at the structure of the data itself, the ARP header, and recap its purpose.
Of course. Even the packets that facilitate this powerful translation are very simple. The ARP header contains just a few key components, including the hardware type, which is typically one for Ethernet,
Right.
and the protocol type, which specifies the network layer protocol being mapped, usually IPv4.
The address lengths are important too for validating that 32-bit to 48-bit conversion.
Absolutely. The header explicitly states the hardware address length, which is 6 bytes for Ethernet, and the protocol address length 4 bytes for IPv4. This confirms to the recipient exactly what size addresses they should expect.
And looking back to the spoofing, the operation cut is deceptively simple.
It is. It's the binary intent of the packet. A 1 indicates an ARP request, the shout, and a 2 means it is an ARP response, the reply. The simplicity of this code is part of the problem. There are no fields for security keys or authentication tokens. It just trusts the 2.
So what does this all mean for you, the listener? Let's summarize the core advantages ARP provides that hopefully outweigh its security risks if we use mitigation.
Well, the primary advantage remains simplicity and automation. ARP makes network management almost invisible. If you know the IP address, the MAC address is automatically determined. End nodes don't need manual configuration to know MAC addresses.
The system just learns the mapping dynamically, on demand. It's a self-learning, self-maintaining communication infrastructure. ARP is truly the network layer's quiet workhorse, translating that logical destination into the physical location so the data can actually traverse the wire.
It's what makes the IP address useful locally. ARP is the essential engine that translates high-level addressing into physical addressing, enabling seamless communication across the local network using both efficiency, that critical cache, and dynamic requests when necessary.
And here's a final thought for you to chew on that brings together the efficiency and the security risk. We talked about the ARP cache timeout, that hidden optimization struggle happening inside your router right now.
Right. If that timeout is set too long, the network avoids constant lookups. But you risk using stale addresses if a device moves, or worse, retaining a poisoned, malicious address long after the attacker has left.
But if the timeout is too short, the network is perfectly current, but you waste bandwidth on constant requests. That balance between saving time and sacrificing safety, or being perfectly safe but wasting resources, is the subtle, constant dilemma facing every network device, all thanks to the humble address resolution protocol.
The real question is, when you rely on something that is intrinsically trusting, what is the optimal length of time you should allow yourself to be lied to?
We'll leave you with that struggle. Thanks for joining us for the deep dive.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo! Haven't you checked out our new book yet? Link in description.
CT